Hello, everyone, and welcome back. In this lecture, we're going to build on the previous topics of definite integrals to introduce one of the most important results in all of calculus. That is the fundamental theorem of calculus. And what the fundamental theorem of calculus does is it unites the two perspectives that we typically take in calculus. It tells us that the derivative and the integral are intimately related to each other through the fundamental theorem of calculus. Now, I know that I just said that we have these two perspectives that we typically take in calculus: derivatives, which are slopes, these are instantaneous rates of change, and integrals, which in the previous lectures we saw are limits of Riemann's sums. But what I want you to always think about when you think about calculus is not derivatives versus integrals, but that calculus is really the study of limits. Think about it. With the derivative, we defined it as the limit of secants approaching a tangent. With the integral, we defined it as the limit of a Riemann sum. As you pile infinitely many rectangles underneath this curve in order to converge to the area. Again, this is with that abstract notion of area that we talked about in the previous lecture. So with that being said, let's go ahead and get started. Okay, so let me just remind you, in the previous lecture, we introduced this shorthand that looks like this, that is just a number, right? There's nothing, this is not a function, it's just a real number. It could be 1, it could be pi, it could be 1 over pi, it could be pi to the pi to the pi, right? It's just a number, but it encodes a lot of information. This encodes the information that we have taken the limit of Riemann sums of the function f of x over the interval a to b. And we remember this symbol right here, this sort of curvy s, is actually meant to be an s, and it means it's to represent a sum for s, and this sum is over the continuous values between a and b. Whereas a Riemann sum, we used the discrete summation term, the Greek letter sigma, to denote that you are summing over finitely many objects. Okay, so before we get into the fundamental theorem of calculus, let me introduce to you an interesting result and an auxiliary result that we are going to use to build up to the fundamental theorem of calculus. And this is the mean value theorem for definite integrals. Okay, so some of you may be familiar with the mean value theorem, as it's typically stated in terms of derivatives, right? It's one of the most fundamental and one of the most famous results in all of differential calculus. And as I mentioned at the top of this lecture, the fundamental theorem of calculus is going to help us unite this perspective of derivatives and integrals. And that means that if we have this perspective of the mean value theorem from derivatives, we also have this perspective of the mean value theorem from integrals. So that's where we're going to start today. We're going to pose the mean value theorem in terms of integrals. Now, let me remind you that we defined the average of a function f over the interval ab as the definite integral just divided by the length of that interval. And so what the mean value theorem for integrals tells us is that there is some point in that interval so that f takes on its average value. So let me write this for you explicitly, and then we'll talk about it. So we have, we're going to assume that f is continuous And we'll talk about why in a moment. So it's continuous over the interval AB. Then for some point C in the interval, we have f of C is equal to the average value of f. Right? So if you just track what I have written, this right-hand side is just the average value of f. Okay, so this may, I don't know, maybe this comes as a surprise. Maybe this is an interesting result for some of you, but this shouldn't be actually that surprising. Think about what this really just says. It says that f eventually, if f fluctuates, it takes on its average value. So let's think about this in terms of the example that was given to us in the very first lecture. We had this idea of water sloshing around in a bucket, and we were measuring on the side of the bucket the height of the water. And we can imagine we're doing this at over a continuous time. So we're doing it fast enough that we can kind of feel like this is just being measured at every instant of time, right? So we're going to add a little level of abstraction to this. But what does this say? We motivated taking the average of this to sort of figure out how much water, what the height of the water in the bucket is when it's undisturbed. Now, if you think of this intuitively, right? If f can never take on the value of its average, that means that sort of its average is like outside of it's either below its minimum value or it's above its maximum value. So somehow there's like more or less water in there than we're seeing being sloshed around, right? And that really doesn't make any sense. So there is a very, very intuitive reason that this is true, but better yet, there's an actual proof, right? There's a proof, there's a mathematical reason why this is true. And let me show you that mathematical reason, or let me show you a consequence of this before I give you the mathematical reason, okay? So one way you can think of this is if you rearrange that formula, if you multiply both sides by b minus a, so let's do this. Oh, so let me take this to be A, this to be B. Let's imagine approximately the average value somewhere in the middle here. Okay, so basically, if you think of this formula in terms of areas, well, then the area underneath, so area, the area underneath the red curve is equal to that definite integral, right? This is what we've been talking about. And then the area underneath the green curve, so this point right here, this is C, this is f of C at its height. The area underneath the green curve is going to be height, f of C, times the base, b minus a. So what does that tell us? Well, from the mean value theorem, so MVT stands for mean value theorem, we have that the red area is equal to the green area. So the area bounded underneath that function is equal to the area bounded underneath that constant function given by the average value. Okay, so this is sort of a geometric way of thinking about this, but how do I actually prove this thing, right? Because so far I've given you an explanation with a water in a bucket and maybe a little picture, but none of these are enough to convince you. Let me actually do a proof. And the proof of this is quite elegant, in my opinion, because it uses the properties of the definite integral. And in particular, it uses property number 6 that we introduced in the previous lecture. So from property 6, we have, now property 6 tells us that the definite integral is bounded below by the minimum of f times the length of the interval. And this is less than or equal to the definite integral. And this is bounded above by the maximum of f times b minus a. Okay, now I'm going to divide through on all 3 of these terms by b minus a. So I'm assuming here that b is larger than a, so that b minus a is a positive quantity. So this tells me that the minimum of f is less than or equal to the average of f, which is less than or equal to the maximum of f. Again, this makes sense, right? Let me show you on my picture. Right here is the maximum of f. Right here is the minimum of f. And right here is the average of f. So this is consistent with my picture so far, but again, a picture is never a proof in mathematics. So how do we get the result? So let me move forward a page so we can start anew. But what this says is that the lowest value that the function attains is smaller than the average, which is smaller than the maximal value that it attains. So, but we assumed f is continuous, which means that f takes on all values between the minimum of f and the maximum of f. You're probably familiar with this result. This is called the mean value or the intermediate value theorem. So we write that as IVT in the same way that I do MVT for the mean value theorem. But let me scroll back for a second. What's in between the minimum and the maximum of f? Well, the average is in between. So this tells us, so hence, there must be a c in the interval a to b such that when you plug c into f, this is equal to exactly the average of the function f. So it's basically the picture that I showed you, but now we used a little bit of logic. We were able to use some theorems from mathematics, right? The property 6 that we showed in the previous lecture and the intermediate value theorem. So this completes the proof. Let's put a little mark down there to tell us we're good, we did it. So let's just dwell on something for a minute. Let me ask you a question, and I know that this is pre-recorded, but why does f need to be continuous? Right, so if you're following along, it might be a good point to maybe pause and think about this problem and ask yourself if you can answer this. Okay, so I'm going to go ahead. So I'm hoping that you did pause, but why does f need to be continuous? you have to be continuous to apply the intermediate value theorem. So the intermediate value theorem requires f to be continuous. Let me give you an example of a function where this would fail if it was not continuous. If I give you, let's say, the function which is 0 all the way up to 1, and then it takes on the value 1 all the way up to 2. Well, in this case, the average value here is actually going to be 1/2, right? Half of the time you're spent at 0, half of the time you're spent at 1. So your average value, I apologize for these not being perfectly straight, but this should be at 1/2, and I should indicate that this is at 1. But there's nowhere that this function takes on the value 1/2. And the reason here is because this is not a continuous function. So we really need that continuous piece. That's the active term in here, right? It has to be continuous, or else this is not going to happen for us. So we remember in the previous lecture, we said there's a wide range of functions that we can take Riemann sums of, right? And we can take that are integrable, that we can take integrals of. And that included more than just continuous functions. That included functions that have finitely many jump discontinuities, just like the function that I drew on the board. But it turns out that if we want to use the mean value theorem, then we require continuity as well. And this is going to be a theme. We're going to require continuity when we talk about the fundamental theorem of calculus. So let's go ahead and do that. Let's introduce the fundamental theorem of calculus. It typically comes in 2 parts. We're going to break it up into those respective parts. And so we're going to start with part 1. So let's say this is the fundamental theorem of calculus. And then we'll say part 1. And this is very, very typical. A lot of people break these things up into 2 different, in the fundamental theorem into 2 different pieces. So let's start with f is a continuous function or an integrable function over, so it's integrable. We can take an integral of it over the interval AB. So that's what we're going to assume. And then we're going to say for any x belonging to AB, so any point between A and B, I'm going to define this sort of weird function. So capital F of x is equal to the definite integral from A to x of f of x dx. This is a weird function, right? It's probably not something we're used to, because when we get introduced to functions, we get introduced to functions that look like maybe 1 plus x squared, or sine of x, or e to the x squared, or e to the x cubed, right? They have a very, very definite form. But this is a weird function, but it is a function nonetheless. What is this function actually saying? This function says, if you think again in terms of definite integrals and areas, this tells you that capital F of x measures the area under the curve from A up to a given value of x. So let's draw that out. So you have to give me little f of x. And then what I do is I give you a value of x, and I ask you to integrate up to that value. So let's say this is my x. And then in this case, excuse me, I can say that my area equals to f of x, right? And the red curve here is little f of x. So it's a very, very abstract function. And it's a function that's determined in terms of a definite integral. So the question is, what are some of the properties of f of x? In particular, we want to ask ourselves, what is the derivative of f of x, capital F of x? So let's ask ourselves this. We're going to use the definition of the derivative to get a sort of informal answer. So what is the derivative of capital F of x? Well, we're good at calculus, especially differential calculus. We can take the derivative using the definition of the derivative, right? The definition of the derivative is given by the limit as h goes to 0 of f of x plus h minus f of x divided by h, right? We probably remember this formula. But let's think about this a little bit informally for a moment, okay? The question is, what is capital F of x plus h? Well, let's go back to my picture above, right? We said that capital F of x is really like calculating an area. So since this is determined in terms of an integral, let's think about it in terms of Riemann sums for a moment. So if I instead, let's use this bright color. If I go up to x plus h, that would be capital F of x plus h would be all of the area in the blue plus all of the area up to that pink line. Okay, so then that tells me that the area in just this little sliver right here is exactly equal to f of x plus h minus f of x. It's the area left over. And so the question is, how do I approximate that area? Well, you can kind of see it right on my picture, right? This is basically a rectangle, especially when h is super, super, super small. So the question is, at the risk of making my picture very, very messy, what is the area that's trapped in there approximately? Well, it's a rectangle. So let me say the area is approximately, well, let's use the left-hand rule for Riemann sums. This would be all the way up to this value right here. This is f of x. So the height of the rectangle is approximately f of x. And the base of the rectangle is x plus h, the right endpoint, minus the left endpoint, x, which is f of x times h. So this tells us that the numerator in this derivative term, this is basically like asking you, the limit as h goes to 0 of f of x times h divided by h, right? So I took that area from right here and I plugged it in to this numerator right here because it's measuring the same thing. And so I get that the h's cancel here. There's no limit anymore. And so you get this really kind of cool relationship, right? This tells you that you expect that this function capital F that's written in terms of a definite integral, its derivative is given by the original function, the function you were integrating. This is exactly what the Fundamental Theorem of Calculus Part 1 tells you. So let me start by writing this on a new page. So this is, we're going to write this as a theorem. And this is the fundamental theorem of calculus, part 1. And what this says is that if f is continuous on the interval AB, then that capital F function that I just defined, so remember, it's the integral from a to x of little f of x. Sorry, I'm using x in the bounds. I should be using t in here. I think I made that mistake back here as well. And it's good that I caught it, yes. We can't be integrating with respect to x up to x. That doesn't make any sense. We need a dummy variable in here. We'll use t instead. Okay, so I apologize for any confusion that might have been made here to anyone. Because the bound of integration includes an x, then we can't integrate with respect to x up to x, right? This is sort of redundant. You're asking for something that you're doing. So we're going to put a dummy variable in there. We'll call it t. Okay, so then if my function f of x looks like this, then this thing is continuous. On AB. And it's differentiable. So it has a derivative at every point between A and B. So in this case, you don't have derivatives at the endpoints, and that comes from the fact that you can only approach the limit in that derivative calculation from only one side for the endpoints. So we typically say differentiable on the open interval, everything but the endpoints. And its derivative is f of x. What this really means is that if you say f prime of x is equal to the derivative with respect to x of this integral term. And this is equal to f of x. So this is a very, very fundamental result, right? Because that last line that I have written there, that ties it all together. Look at that. It's a derivative and an integral, and they are sort of canceling each other out in a weird way, right? You're taking an integral of little f, and then you're taking a derivative of it, excuse me, and you find that you get back what you started with. These are inverse operations of each other. One, you can think of, I like to think of derivatives as sort of going down, and that comes from the fact that derivatives of polynomials decrease the power. Then you can think of integrals as going back up. And so what you've done here is you've gone up, and then you've went back down. So you've gotten back to where you started. Before we prove this thing, let's do a couple little examples. So example 1, let's start with the function, the integral of a to x of t cubed plus 1 dt. Then the question is, what is the derivative of this thing with respect to x? Well, dy dx, this is the derivative of this integral term, a to x, t cubed plus 1 dt. If we look at that formula that's written at the top of the board, well, clearly the integrand, t cubed plus 1, is continuous everywhere, so it doesn't matter what the value of a is. And what it basically says is take the integrand, f of t, so t cubed plus 1, and just replace the t's with x's. So this gives me a nice x cubed plus 1 here. Okay, let's look at another one. let's say y is equal to the integral of x to 5, 3t sine of t. Okay, well, we want to take a derivative of this thing, but the first thing that you can see is that this isn't exactly in the form that we would have expected, right? Because if you think about the capital F of x that's given here, the integrand x has to be at the top. It is the top bound of integration, not the bottom. But luckily, remember we have all those properties from last lecture. And in particular, the first property told us that if we can flip the bounds of integration by simply negating the integral. So this is the same as going from 5 to x with the minus sign out front of 3t sine of t dt. And this tells me that if I want to take a derivative of this thing, now it's clear sailing, right? This becomes d dx of minus 5 to x 3t sine of t dt. The minus can come out front, so I get minus the derivative of this thing. And now I'm in familiar territory. Now I can apply that fundamental theorem of calculus, part 1. And this tells me that I just need to replace the integrand, the t's in the integrand, with x's. So I get minus 3x sine of x. Beautiful, isn't it? Okay, let's look at another example. Let's do y is equal to the integral from 1 to x squared of cos of t dt. Okay, this one's a little bit more hectic looking, right? Because the fundamental theorem of calculus part 1 tells us that we can only take derivatives when the upper bound is just a single variable, like x. But in this case, we're integrating all the way up to x squared. So what happens? How do we view this? Well, luckily we have a ton of other techniques for taking derivatives. And we can introduce a dummy variable in the middle here to really view this thing as a composition of functions. And when we think of composition of functions and derivatives, that means that we have to use the chain rule. So let's really think of y as a function of u that says, if I give you a value of u, you integrate up to that value of cos of t. And the value of u is determined by a value of x that I give you. So I give you x, you square it, that gives you u. Now you take that u value and you put it into y, and that gives you a y value. So now we can view this thing as a chain rule problem, as a composition of functions, because really the original function y is y of u of x. And so the chain rule tells me that if I want to take a derivative of y with respect to x, this is the same as the derivative of y with respect to u multiplied by the derivative of u with respect to x, right? This is just the chain rule, nothing fancy. Okay, so let's calculate some derivatives. So dy du, this is just the derivative of the function of 1 to u of cos of t dt. Now, this is the fundamental theorem of calculus, right? I dressed it up a little bit. I used the independent variable now is called u, but that's okay, right? It was called x in the theorem. I could have called it z. I could have called it p. I could have made up my own symbol. I could have drawn a giraffe and used that. It doesn't matter, right? It's just a placeholder for a number. And so this tells me that the derivative of u is really just, or sorry, the derivative of y with respect to u is really just cos of u here, just applying the fundamental theorem of calculus. Similarly, the derivative of u with respect to x is equal to the derivative of x squared, which is a nice, easy 2x. So this all together tells me that the derivative of y with respect to x is equal to cos of u times 2x. But let's think about something for a moment, right? The original problem had no u's in it at all. Nobody asked me about a u, nobody gave me a u, so nobody wants to hear about a u at the end. I put that in there to make my life easier, but a correct answer to this has to get rid of the u's. Now, luckily, u is just equal to x squared, so I can simply substitute that back in and give you the derivative of y with respect to x as a function of x only. So I'm going to move the 2x into the front. I like to put my trigonometric terms on the end, and this gives me cos of x squared. There is my derivative just using the chain rule. So now we have another addition to the list of rules that we can use for taking derivatives, right? We've got the product rule, we've got the chain rule, we've got the quotient rule, and now we've got the fundamental theorem of calculus, part 1. Now, let me give you one more example that we can kind of speed through, but it puts everything together. So this will be 1 plus 3x squared as the lower bound, 4 as the upper bound. The integrand is 1 over 2 plus e to the t dt. And so the first thing we're going to do is we're going to use property 1. Again, when you're doing this yourself, you don't have to list the properties, and I probably won't going forward, but it's important for us to see sort of where these things come from. So this gives me 4 to 1 plus 3x squared, 1 over 2 plus e to the t dt. And in this case, you're again going to use the chain rule. So I'm going to sort of skip through the steps. I'm going to jump. And I want you, if you're following along at home, to try and do this on your own, to try and work through the proper chain rule steps here. So the first thing that you're going to do is you're going to differentiate using the regular fundamental theorem of calculus and put that upper integrand into the upper bound into the integrand. So you get the minus floating through 1 over 2 plus e to the power of 1 plus 3x squared, and then multiplied by the derivative of the upper bound there, which is going to be 6x. If you want, you can clean this up a little bit, minus 6x over 2 plus e to the 1 plus 3x squared. Beautiful. So now that we've played with a little bit of examples, let's do the proof of the fundamental theorem of calculus. So proof. So the fundamental theorem of calculus 1, FTC 1. Okay, let's do it properly, right? I gave you that heuristic explanation where I said that you can think of it as a rectangle and you know, bada boom, bada bing, and everything sort of makes sense, but it's not perfect, right? There's a lot of this going on, you know, should equal, but maybe doesn't. Let's do it properly. Okay, let's calculate out the derivative. So f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. This is going to be, if we just actually take the definition of capital F of x, let me pull the 1 over h out front. This is the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. And you can use property number 5 from the previous piece, or from the previous lecture, to break up this integral right here. So let's say this integral is actually equal to the integral from a to x of f of t dt plus the integral from x to x plus h f of t dt, right? This is property number 5. And so you can see that this term right here is going to cancel with that term right there. And so what are we left with? We're left with the limit as h goes to 0 of 1 over h, and then the integral of x to x plus h f of t dt. Okay, this is sort of shaping up nicely. But the question is, how do I finish this? Because it's not quite clear to me what's going to happen as h goes to 0. Well, we started this lecture with the mean value theorem. Did you think that I forgot about it? Of course not, right? This is where it's going to come in. It's going to help us prove this. So we can think of this thing as being the average of f of t. Or sorry, yes, of f, and the 1 over h out front as well. And so that tells me that from the mean value theorem, MVT, there is C in the interval x to x plus h such that f of c is equal to this average. Remember, we assumed that the function is continuous, so we can do this. Okay, so that tells me that if I go through this chain here, this tells me that the derivative of f prime of capital X, this thing is equal to the limit as h goes to 0 of f of c. Great, right? I got rid of the 1 over h. That's always the biggest headache when you're doing these derivative problems. So here's what happens. C belongs to this interval right here, x to x plus h. So what happens as h goes to 0? Well, this interval collapses down on itself, right? It goes from x to x plus h, is slowly shrinking. And so eventually what happens as h goes to 0? There's only one point left in there, x, right? The left and right points collapse down on each other, which means that if c is in that interval, the only point that that's left for it to be is x. So we get that this thing is equal to f of x. So this gives us exactly what we said in the statement of the theorem. It says that if you take the derivative of that capital F, then it is equal to little f. And since this holds at every single point in x in between a and b, that gives us differentiability everywhere in that interval. And then because the derivative is continuous, we also have that this thing is purely differentiable between a and b, and then continuity just follows from the fact that the original function was continuous. So this is nice, right? It inherits properties of the original function, little f of x, but also gains them, right? By integrating, by moving up the ladder, we made this thing sort of more smooth, or we made it smooth because now it's a differentiable function. It didn't have to be differentiable. Little f didn't have to be differentiable initially. So let's mark off that we did it. We proved it. Okay, so I gave you the fundamental theorem of calculus part 1. The question is, what is the fundamental theorem of calculus part 2? Well, let me give you the theorem and we will talk about it. So FTC, fundamental theorem of calculus, part 2. So we're going to say, again, if f is continuous on AB, so the same assumption as before, and capital F is an antiderivative of little f, right? So that means that if I take the derivative of capital F, I get little f on this interval. Then the definite integral of f of x from a to b is equal to capital F evaluated at the endpoints. Think about how cool this is, right? Again, we're relating integrals to derivatives. This is a really weird thing to say, right? It says that if I know the antiderivative of the function I'm interested in, then I can find out what the sort of area under the curve is, right? What is the relationship here, right? It's a very, very strange thing to think about, but this exactly tells us. It says, if I know the antiderivative, then I don't have to compute a Riemann sum. That's a huge pain, right? It's a lot of work. No, I just need to evaluate the antiderivative at the endpoints. So this gives us a relationship for definite integrals. The previous part 1 gave us a way of constructing antiderivatives, okay? So we should think about this in an appropriate way, right? So that this part 2 tells us that if we know an antiderivative, but part 1 gave us a way to find that antiderivative, okay? So you should keep these things in perspective. Let's do the proof here. So the first thing is that we need an antiderivative for this function, okay? So, well, the first part of the Fundamental Theorem of Calculus, so FTC part 1, tells us exactly what I just said, that if capital G of x is given by this, a to x of little f of t dt, then G is an antiderivative of little f. What this tells us is that this really characterizes every single possible antiderivative, because then we have to have that f of x, capital F of x, and little g only differ by a constant. So some real valued constant. That's it. This is actually a consequence of the mean value theorem, right? So it says that you can characterize antiderivatives up to adding on a constant. So, okay, then that tells us that from the Fundamental Theorem of Calculus part 1, f and g are both continuous functions. They're both differentiable on a to b. And so let's do this. F of b minus f of a. This is going to be, let's just use this, g of b plus c. So I'm just writing out the definition, minus g of a plus c. You can see that those constants are going to cancel each other out. So it didn't even matter that we had them in there, right? We just needed to be precise. And so this gives us g of b minus g of a, which, let's write it out. We have the definition of g of x. So substituting in x equal to b gives us the integral from a to b. And substituting in x equal to a gives us the integral from a to a. But from property number 2 of the integrals that we saw in the last lecture, this thing is equal to 0. And that's property number 2, if we want to label it. And so this gives us exactly what we said we were going to get. So that gives us the proof right there. Isn't that great? That's an excellent way to do this. And so sometimes what we do, so just for notation here, we write f of b minus f of a. Oh. A lot of the times we'll write this as f of x and then align a to b. So similar to how the integral is set up, saying the upper and lower bounds on this integration, this means the value at the top part of this line, so the b, subtracted by the value at the bottom part. And so let's just do a couple of examples before we finish up here. So examples. So let's find the area or the definite integral from 0 to pi of cos x dx. Well, what function differentiates into cos of x? Again, we saw that in the proof of the fundamental theorem of calculus part 2, it doesn't matter what the constant is on the end. We just need to know the function. And so in this case, there's only one function up to a constant, and that's sine of x. So this is going to be equal to sine of x running from 0 to pi, which is sine of pi minus sine of 0, which is 0 minus 0, which is 0. So the sort of abstract notion of area in this case underneath cos of x is equal to 0, right? It spends as much time above 0 as it does below 0 in terms of these areas. Okay, let's take a look at another one. So minus pi over 4 to 0 of secant x tan x dx. Well, the question is, what function differentiates into secant x times tan x? So we might have to rack our brains a little bit for trigonometric derivatives here, but I'm going to spoil the surprise. In this case, it's equal to secant x. And in here, we're running from minus pi over 4 to 0, so that we essentially we get secant of 0 minus secant of minus pi over 4. So we might have to look up some trigonometric identities here. But in this case, the first term is equal to 1. The second term is equal to the square root of 2. And that's not going to get any nicer looking, right? So I'm going to leave it just like that. But think about how great this is, right? This tells us that we don't have to do Riemann sums anymore, right? We spent all of this time getting very good with derivatives. And it's finally paying off, right? Because now we can intuit what antiderivatives are going to be. And that means that we can apply these fundamental theorems of calculus in order to greatly simplify these integral calculations. And what we're going to see moving forward throughout this class is all the different ways that we can use integration to understand much more complicated and much more general, much more applicable problems than, say, just finding this sort of abstract notion of area underneath or bounded between the x-axis and a curve. Okay, see you next lecture.